So what we are going to be doing today, what we shall be doing, basically is to resolve some questions. And this question one, and the question one says, using the voltage divider rule, determine the total current, the total resistance in this figure, which is this circuit we are seeing, when V of R1 is 10.29 volts. Find VR2, VR3, and VR4. Then the I2 of that question lists 6 types of transformer and where they can be used in your field. 3, define magnet and briefly explain 3 categories of magnets. And this is the question, and this is the solution. First of all, when you are given the question, you have to list the known variables. And what are the known variables? You are given VR1. You are given the total voltage from the circuit. This is the total voltage here. Then you are given R2 900 ohm. You are given R1 1.2 kilo ohm, which is 1,200 ohms. You are given R4, which is 1.5 kilo ohms, which is 1,500 ohms. Then what you are looking for is R1, total resistance, which is R of T, total current, V of R2, R3, and V of R. Please, if people should mute your mic. Mute your mic. Are you hearing me? So,
yes, sir.
From the solution, we know our basic law, which is the Ohm's law. We apply the Ohm's law to resolve this. And from that Ohm's law, we states that current, which is total current, is equals to V of T over R of T. This is the Kirchhoff's law. And by applying it with the Kirchhoff's voltage law, V of Rn equals to I total times R of n, where R total, are you seeing, is the formula for I total. This is for those in biomed and P&O. They should pay more attention. R total for a series circuit is R1 plus R2 plus R3 plus R4. So, which implies that the V of R1, this voltage drop here of R1, is equals to total voltage over RT times R1. That is, you've used the voltage divider rule to get the resistance of this part, this resistance. And because we know our distance, because we know our total, we know our resistance apart from the R1, what we are going to do is to implement this, further expand this formula, where we now expand our R of T and put it in this equation 5. Then if we do that, we put our variables. These are our variables. 10.29 volts is equals to 72 volts all over R1 plus 900 ohms plus 1,200 ohms plus 1,500 ohms. So when you cross multiply, what we will have will now be 10.29 volts over 1 is equals to 72 volts times R1 all over R1 plus 3,600 ohms. So let's multiply and open this bracket. We have that. I think somebody is making noise in the background. So what we are going to have will be 10.29 volts times R1 plus 37,044 is equals to 72 volts times R1. We collect the like terms. And by collecting the like terms, it will mean that 72 volts times R1 minus 10.29 volts times R1 is equals to this 37,044. And when you further make R subject of formula, we have 600.2917 ohms. So we've determined our R1. And from that R1, we got our total resistance using this formula for total resistance to give us 600.2917 ohms plus 900 ohms plus 1,200 ohms plus 1,500 ohms. And our total resistance becomes 4,200.2917 ohms. So then from the equation, we are told to look for the total current. From the equation, we've gotten our total resistance and we know our total voltage. We can say that the total current will now be 72 volts divided by 4,200.2917, and that gives us 0.17142 ampere. Or you can say that the answer is 17.142 ampere. Then, using the equation, we can now, using the equation 2 that we've stated before, this is the equation 2 I've shown you. This is the equation I showed you, this equation. If we use it, we will now say that VR of 2 is equals to I total times R2. So what you just need to do is that you multiply the total current by each of the individual resistance. Like the R2 is 900 ohms. When you multiply 900 ohms by 0.01742, you will get 15.4278 volts. And likewise for VR3, 1002 will give us 20.570 volts. For R4, will give us 25.713 volts. And to prove that what we've gotten is the right answer, using the Kirchhoff's voltage law, so this 72, which is the voltage of the battery, is equals to 10.29 plus 15.4278 plus 20.5704 plus 25.731713, and we have 72.0012. So which means approximately what we have is corresponding with the voltage input from the cell. Let me just admit some people. So that's that for part of the question number 1. For the transformer, for the transformers, we have step up and step down transformer. And we use the step up and step down transformer for home appliances to increase or decrease voltage, or for the power tools, for those of you that use power tools, those of you in biomedical, in each of the electronic components or the basic biomedical equipments, like the suction, like the centrifuge, or like the hematocrites. It always uses voltage transformer to step down the voltage or step it up. Then we have the auxiliary transformer. So it steps, this is a step down transformer connected to power generators. What it does is to stabilize the frequency and power the equipments in the power generators. We have auto transformer, we have a distribution transformer, then we have earthing transformer. This one is, we use it to do the earthing out the power line, to make sure that the power line does not shock, or the poles. We have phase shifting transformer. Then transformers are classified in different ways. We have three-phase transformer, we have single-phase transformer. And again, we have we have instrument transformer. Depending on the application you use the transformer, so it determines the name that we give transformer. We have power transformer. We equally have current transformer, and we have voltage transformer. So for question III, that is define a magnet. We say that we've done this thing as a quiz, that magnets are those materials that has the ability to attract other materials around its flux. It has north and south pole with a continuous line of force, which we call the magnetic flux line, which originates from the north pole to south pole. A magnet repels the like poles and attracts the unlike poles. Then the three categories of magnetic materials, we have the diamagnetic materials, we have the paramagnetic materials, and we have the ferromagnetic materials. So for the diamagnetic materials, they have the permeability that are less than permeability of free space. They create an induced magnetic field in them, which are opposite to magnetic flux, thereby creating a repulsive force. Then for the paramagnetic materials, these materials has the permeability slightly above permeability of free space. They have magnetic dipole moments that are permanent. They are weakly magnetized in the direction of the magnetizing field. So for this one, can magnetize. But the issue is that once you remove the something that is influencing the magnet, something that is causing that material to magnet, it will lose its magnetic property. Then for ferro, it has a strong magnetic property. The magnetic material does not easily lose its magnetizing force, and the permeability is high above the permeability of free space. Then for question 2. Question 2, this was part of what I'm supposed to teach you in class concerning electric motors. I say find the speed of 8-pole electric motor whose frequency is 60 Hz. Then the II is determine the flux density of a magnet whose cross-sectional area is 1.82 times 10 raised to power minus 4 meters square. And the number of flux, 12 times 10 raised to power minus 2 Weber. Determine the instantaneous voltage of a sinusoidal circuit at 25 degree, 30 degree, 45, 75, 85, 115, 165, 175, 185, and 227 angular displacement, when the maximum voltage is 180 volts. So, for the first question 2I, using this formula, already we've noted our variables, the ones that we know. The number of poles, which is N, is 8 poles. Then frequency is 60 Hz. And speed, S, is unknown. So, using this frequency equation, which is F is equals to number of poles times the speed of the electric motor divided by 120 degree. This angle is the angle of separation between the phases of electric motor, the phases of the armature and the stator winding. So therefore X is equals to 120 times F over N, and we have 900 revolution per minute, which is RPM. Then for question 2II, we have the number of flux, we have the cross-sectional area, and we are looking for the flux density. And by virtue of our equation, the flux density is equals to the number of flux over the cross-sectional area. And from what we have here, the flux density is 659 times 59.3407 Weber per meter square. So you notice that this one is kind of much easier, but it's still part of what I taught you people in technology. No, this is the magnets we are doing. So coming for this one is simple, but I know some of you will likely feel it. But if you look at it very well, it's just for you to add this angle, and take the sine of it, multiply it by this maximum voltage. And from what I did here, we have that from what I did, we have that 180 times sine 25 is 76.0173. You can still, maybe when you check when you go back through the YouTube video I'm going to upload, you will just check all these things. The same applies to this 30, and the same applies to 45. The same applies to 75, and these are the things that you'll be getting. So you likely might get minus, and you likely might get a plus. So depending on the angle you get, this minus is necessary. Please don't say that the minus is not necessary. You need to put it. It shows that is on the negative side. Is a repeating waveform. So this is another question. And this question is question number 3. And for question number 3, we have a circuit attached to it. It says determine the total resistance and total current, I of t, of this circuit using the Kirchhoff's current law. Solve for I1, I2, I3, I4, I5, and I6. What is the output voltage of a transformer whose primary voltage is 54 volts with transformer ratio of 0.25? Then he went further to say, using your answer in this II and primary impedance of 20 ohms, determine the primary and secondary currents. Number of turns are both the primary and secondary. And finally, the load impedance of the transformer. So for the first one, we list what we have here, which is voltage total test 2 volts, R1 180, hold on, R2 220, R3 319, R4 475, R5 665 ohms, R6 and 800 ohms. We are looking for the total resistance. We are looking for the total currents. We are looking for I1, I2, I3, I4, I5, and I6. And the solution to this is using our Ohm's law. And using the Ohm's law, we know that V over T equals to I. But Kirchhoff's current law states that the total current entering a node is equal to the total current leaving that node. So we can say that I total is equal to I1, I2, I3, and I to any number it is. Then we say that equally recall that from IN, that is I of 1 is equal to VT all over R of 1, where N is 1, 2, 3, 4, 5, to any number you feel. So, and the resistance, I've done this thing for you, those in tech and those in biomed and P&O. The formula for total resistance is inverse of total resistance equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over till the infinite, the number, which here is 6. So we now fix our variables. We now have that 1 over 180 plus 1 over 220 plus 1 over 390 plus 1 over 475 plus 1 over 665 plus 1 over 800. Please, I think we will have to go through another link so that just stay calm. I will create another link. We will join. This one is going to stop soon. So I have told those in tech that if you are given this, don't use a complex formula. Just take the inverse of each of these, like 1 over 180 is this, 1 over 220 is this, 1 over 390 is this, 1 over 475 is this, 1 over 665 is this, and 1 over 800 is this. Add them. Look at their final addition. You take the inverse of this, your answer, which is 1 over 0.017524 equals to 57.06460 ohms. It becomes our total resistance. But if you feel like you want to use this particular formula, this is the formula, you still get to the answer, but it looks more complex because when you start to fix and multiply these variables, this is what you are going to have. And by nature of your exam, you might not be able to calm down to do these additions and get your answer, though they are going to lead to the same answer. So this becomes our own. It's still the same thing with the first method we used. Then the total current we have will now be 32 volts all over 57.06460 ohms, giving us 0.56077 ampere, or we can say is 560.779 milliampere. Then for I1, we say that voltage, total voltage all over R1, the I1 will be 0.17778. And this is our answer. For I2, total voltage over R2 will give us 32 volts over 220. That will be 0.14545 amp. I3, this is for I3, that's 2 over 390, which will give us 0.8205. For I4, that's 2 volts over 475 will give us 0.06737. For I5, we have that 32 volts over 665 ohms will give us 0.04812 ampere. And for the 800 ohm, which is I6, will give us 0.04 ampere. So I think this one settles this. Then for the impedance, we've listed the variables they have given us. You will see the variables here. We start to put in the variables. Already we know our transformer ratio to be 0.25. And we know from what we did in class that the square of the transformer ratio, inverse of the square of the transformer ratio is equals to the impedance of secondary all over primary impedance. And from that, we have that the secondary impedance will now be the square of inverse of the transformer ratio times primary impedance. And we have that the secondary impedance is 1 over 0.25 square times 20 ohms, which is equals to 16 times 20. And that gives us 320 ohms. For the primary current, since we have our primary voltage and our primary impedance, what we are going to have as the primary current will now be 54 volts over 20 ohms. And that gives us 2.7 ampere. For the secondary current, since we have that the secondary voltage is 216 volts, 216 volts divided by 320, we have it to be 0.675 ampere. And this becomes our current. Then for the secondary, what's it called? Have I solved? Okay, we got this here. I think I jumped. Sorry, I jumped. This is how we got the 216 volts, please. This is question 3II before we now went to III. So you should look at it very well. This is how we got 216 volts. So for the secondary current is alpha times IP, which is 0.25 times 2.1 ampere. And we have 675 milliampere. So you can see it corresponds with this we have here. It corresponds. Then for our transformer ratio, these are the tons. The transformer can have 25 tons over 100 tons, which is 1/40. So the primary tons is 25 or 1 ton, while the secondary ton is 100. But normally it's 25 at the primary and 100 at the secondary.